encounter, Voyager sent back news of the discovery of an extra 7 satellites. When we arrived, the press room at JPL was empty, waiting for the international media to arrive. Ed Stone, project scientist, was, obviously, looking forward to what Voyager would reveal in the next few days.
Uranus will be the most remote object yet visited by a spacecraft, and as a result we know a lot less about it than we knew about either Jupiter or Saturn before our encounters.
What about the lack of surface features?
Well, Uranus is a giant gaseous planet like Jupiter and Saturn. Unlike them, it's tipped on its side with the sunlight incident on currently on its south polar region. And one of the things we would hope to study is the weather in this unique system where the polar regions are warmer than the equatorial region.
What are your main hopes for the mission, really?
Well, we want to study the planet, we want to study the rings, the satellites, and find out whether there's a magnetic field and any trapped radiation associated with that magnetic field.
And, of course, this is the only probe scheduled to pass Uranus in the near future.
It's the first and the only one in the near future.
Well, I'm afraid we can't show you the actual spacecraft. It's rather a long way away now. So we can do the next best thing and show you a full-scale model. And we're delighted that Dick Laser, who's the project manager, has joined us. Of course, this high-gain antenna is the vital link, is it not?
And that's right. This antenna is a parabolic dish which is 12 feet in diameter, and it must be kept pointed at the Earth all the time that we need to communicate with the spacecraft.
The magnetometer is this silver box located right up here, and because of the size of the building that we're in, the magnetometer cannot be fully extended, and so it is in its launch position right now. When it was extended right after launch, it sort of popped out like a slow-motion jack-in-the-box with Jack's head being the magnetometer, and it goes out 40 feet out into space. The reason that it sits so far out in space is because we want to measure the magnetic field of the environment that we're in, not the magnetic field of the electronics here in the spacecraft.
And then, of course, on the other side of the spacecraft, we have the all-important scan platform, the one thing that has given a bit of trouble before now.
That's right. Now, what happened at Saturn when we crossed the ring plane is that the gear mechanism located up here actually got stuck. It bound together. The lubrication in that actually failed on us. We figured out the right way to do it. We figured out if we use this actuator motion very sparingly, that in fact we have a high probability of successfully making it. Now on this platform we have a series of instruments that we call remote sensing instruments. They're not measuring something in the environment of the spacecraft, but rather they're looking off at a target in a distance. Specifically, up here we have the 2 imaging cameras, or the television cameras. We call them wide angle and narrow angle, but in fact what they really are is a telephoto lens and a super large telephoto lens. And so there's actually 2 separate imaging systems there. Located down here we have a device called a photopolarimeter. It's basically a light intensity measuring device. This is the infrared instrument right here, and then we also have an ultraviolet instrument. Now, on the boom that connects the scan platform with the main body of the spacecraft are the last 3 instruments, the ones we haven't talked about, and they are specifically the plasma instrument. It measures the energetic plasma in the vicinity of the spacecraft, the low energy charged particle instrument, the one closest to the antenna, and finally the cosmic ray instrument.
The signals from Voyager are picked up by the 3 main receiving stations, Goldstone, Madrid, and Canberra. Actually, at this time, we should really say 4 stations, because Australia is the key. The Voyager is going to be almost overhead from there during the vital period. And so the great 210-foot radio telescope at Parkes has been called in to link with Canberra in order to get as much amplification as possible of the almost incredibly weak signals. After that, the signals come here, to this building. And this is the DSN, or Deep Space Network, the real heart of the entire mission. It's an incredible place, like science fiction come true. It's in operation for 24 hours a day throughout the entire year. Here, signals are received, and from here, commands are sent out. Of course, it does take time. Radio waves travel at the same speed as light, 186,000 miles a second. And at the moment, it takes 2 3/4 hours for a signal from here to get to Voyager 2, and of course, 2 3/4 hours for a message from Voyager 2 to reach the DSN. And bear in mind also that tiny amount of electrical power actually being received from the probe, not nearly enough to light up a torch bulb for a fraction of a second. It's not merely a question of tuning in and getting a picture. And from here, the raw data are sent on to the image processing laboratory.
The
pictures really represent a mosaic of individual intensities, and therefore there's a number associated with each point on the picture. So as the pictures come back, we of course look at them to get some first order idea of what is in them, but the real science comes from the analysis, the computer analysis of the images themselves.
One of the imaging team here at JPL is no stranger to the sky at night, Dr. Gary Hunt.
Now what we want to do is enhance this image to see if there is any detail, because you can see at the moment it looks no more than a billiard ball with virtually no contrast at all. If we do some processing to bring out the detail, we'll now show you just how much information is contained within this particular image from Uranus. Any specks on the faceplate of the camera will show up as artifacts in the image. And one good example is this ring. Here it comes, right. Now, this, Patrick, is a highly filtered image, and okay, the dust ring is still very much present, but here is a very pronounced white mark and another one. This is a very important image. This, in fact, is a discovery image. In a sense, this is the first time that we have seen well-recognizable cloud features in the atmosphere of Uranus from the Voyager mission, and this dark feature behind it is consistent with perhaps an absence of cloud. Our next job is to track those features to determine the rotation rate of Uranus. We are into the incredible discovery mode that even the length of the day on this planet is not known. So we'll be following over the next few days how these cloud features move, how they move relative to each other. Are they moving at the same speed? Are they moving at different speeds? Whether there are cloud features at other latitudes as we move towards the polar region itself.
One of the important experiments on Voyager 2 is the infrared. One of the scientists deeply concerned with that is Dr. Dale Cruikshank. What are you hoping for from Voyager 2?
We've only had a very brief look and an imperfect look at Uranus in the infrared wavelengths of the spectrum, partly because of the gross limitations of our own atmosphere and because we're so far from that planet. But with the spacecraft on the scene and with very sensitive instruments unimpeded by the Earth's atmosphere, it should be possible to make very detailed measurements of the temperature of the planet, not just globally averaged as we can do from the Earth, but in individual locations across the planet's atmosphere. Another very important aspect of this infrared instrument aboard the Voyager spacecraft is that it has a spectral resolution capacity, which we can't really do very well at all from the Earth. This spectral resolution capacity will allow us to search for specific molecules in the atmosphere of the planet, and also to help us understand something about the detailed composition of the planet's atmosphere. In particular, we're confident that most of the atmosphere of Uranus is made of hydrogen, as is the case with all the outer planets, but there must be a fair amount of helium mixed in there as well. Now, the ground-based observations suggest that there may be as much as even 40% helium, and while that seems a bit implausible from what we know about the other planets, we're certainly very interested to either confirm or refine that kind of an estimate. It's my own suspicion that the estimate will come out substantially less than 40%, and certainly the instrument that we're standing in front of here on the scan platform will give us a good opportunity to find that out in great detail.
We are now 3 days away from closest approach. Voyager 2 is 2.5 million miles from Uranus and closing in fast at the rate of something like 1 million miles a day. And we've already got the first picture that really shows something on the planet's surface. Excited, Gary?
Very excited. I think when you look at these first pictures, the new information which stands out is the fact that Uranus does appear banded. We've seen the bands on Jupiter and Saturn. There's now evidence of banding on Uranus, even though we're flying towards the South Pole. It looks very odd because of the strange orientation. But this is the first major discovery that we can see in the images.
And the false colour picture, that black area, is in fact the pole.
Yes, the pole area is the darker area, and in fact there are some suggestions of the candidate clouds that we're looking at. It's very cold here, many hundreds of degrees below freezing point of water, and we're probably looking at things like acetylene as some of the high-level clouds that could be composed there. That will be the material we're searching for as the days progress and looking for small-scale feature within the clouds themselves.
When we first saw the press room, it was a quiet place. It's anything but quiet now, as representatives of the media from all over the world gather here for the first of the daily press conferences that will be held until the active part of the mission is over.
Good morning. I'm very pleased to welcome all of you to JPL. I'm sure, like me, most of you saw the 9 o'clock status report this morning, and you were reassured, as I was, that Uranus is still there.
2 days now to closest approach, and Voyager is 1,700,000 miles away from Uranus. And that first press conference certainly came up to expectations. To my mind, the most fascinating picture of all was the one showing those two tiny shepherd satellites. What do you make of that, Gary?
Really, that's a very exciting picture. We've now got the Epsilon ring with these satellites on either side of it, obviously keeping the ring particles from diffusing away. They're very small satellites, Patrick, and very dark as well. And I think that's the surprise, that we're finding so many fragments around Uranus which are small and very dark. But certainly there is an anticipation that perhaps within the spaces of the rings there are more very tiny moons.
We mustn't forget the planet itself. And we do have one very interesting false colour picture.
This colour picture, you may remember, is one that we worked on a day or so ago and gives an indication just how long it takes to process the data. This is looking again at the South Pole, which appears brown, and remind people those rings are in fact false effects that come from the camera's optics. Forget the donuts that you can see there. But if you look towards the equatorial regions, which are blue, you'll find a white streak. That is a discovery picture, the first time we've seen the clouds in the atmosphere of Uranus, and we're now getting some indication of how fast things are moving. That particular cloud has a rotational period of about 16.25 hours.
Isn't it strange that on Uranus the poles are actually warmer than the equator?
Yes, the meteorology is going to be very strange, but the other extraordinary thing is that the South Pole is in sunlight, and the temperature there will probably be the same as the North Pole, which is not in sunlight.
Why is that?
Because the atmosphere is like a huge ocean and cools very, very slowly. In other words, it retains its heat. So that we are expecting extraordinary meteorology, but now there are several indications of motions, not only the white streak we can see in this particular cloud, at a slightly smaller latitude towards the equator, there are features moving at 17 hours, and then we come to 44 degrees, we're finding other cloud spots moving a little bit faster at about 15 hours. So in fact, there is a clear indication of very fast motions in the atmosphere of Uranus.
Uranus is now starting to show considerable surface detail. One thing it's not showing at the moment is any trace of a magnetic field.
That is a puzzle. But at this moment, we're still just a few days away from encounter, no evidence of a magnetic field, a very great puzzle, and many of my colleagues are working hard to investigate whether there's a chance of seeing one soon.
As good as these latest pictures are,
The pictures of the moons rarely catch the headlines, and they're of special interest to Merton Davies.
with Uranus,
Well, they're beginning to get very exciting. We're beginning to see surface features on quite a few of them. One of the surprises is that Umbriel is darker than any of the others, and so far we have not seen very much detail on Umbriel. The closest one to Uranus is Miranda, and that's the smallest, and we haven't seen much detail. We're just beginning to see a few spots. Ariel is beginning to show us lots of markings. We've been able to monitor the rotation, which was one of the things we wished to do, to make sure that these are in synchronous rotation as expected. And we've been able to monitor the rotation on Titania. There are quite a few spots, and even things which might resemble some surface features, but we can't identify them for sure yet. The farthest one out was Oberon, and on this one we do see enough in the way of surface features that remind you of maybe a large basin or something like that, which we would see on the Moon or Mercury.
We are now only 1 day away from closest approach, and Voyager 2 is within 1 million miles of Uranus.
Good morning. And yes, there is radio emission from Uranus.
It's a very, very important result, Patrick, because we were puzzled that so far not to have any indication of radio emissions from Uranus, and perhaps the interior of Uranus also is electrically conducting, produce a small but significant magnetic field. In terms of what we're looking at, when we look at the planet, the South Pole, optically, is the pole that we're looking at, but the magnetic field that we're looking at, in fact, is the North Pole, and the difference between them is that we make up the definition of the magnetic poles by the way in which the charged particles spiral towards us along the magnetic field lines, and that is the convention we're following. So we're looking at the South Pole, but the magnetic field we detect is the North Pole. if we can track the particles in the magnetic field, we'll actually get the precise length of the day for Uranus, the so-called solid body rotation. So the cloud winds that we have been talking about, we can now refer to this magnetic field. We'll be able to say whether the clouds are moving to the west or to the east when we look at them on the planet. And this is very, very important, therefore, not just for the interior of the planet, but also for understanding the weather systems too.
When you have a false colour picture, there's some red near the bottom of the image.
Yes, the reason for that is that the colour pictures are produced by adding together pictures taken at different filters, the red, the blue, and green, and so on. And when you observe Uranus through each of these filters, the cloud characteristics are different, and therefore the planet is slightly different itself towards the limb. The properties of the clouds alter. So in fact the radius of the planet is different in each one of those colours.
We have now, too, the very first picture that I think that shows all the 9 rings. Do you think there are any more rings?
Well, if they are, they must be extremely faint, and we can't see them yet. I think what we will be searching for in the data is evidence of other shepherding satellites. We have this one pair around the Epsilon ring. There are theories that suggest that each of the rings will have shepherding satellites to keep them in position. And they must have something to keep them organized because the particles are so fine.
Today, January the 24th, marks the climax of the whole mission. And this morning's press conference started off with a momentous announcement.
Well, just about 2 minutes ago, Voyager 2 passed through its closest approach to Uranus.
So in fact, Voyager has now made its closest approach to Uranus at only just over 50,000 miles. And Gary, everything's going perfectly.
Yes, it's been a remarkable success. It'll be some hours before we see the data that came back at that time, but I think we're all jubilant that after this very long flight we have a totally healthy spacecraft and a mass of exciting data.
Including, of course, the new data about the Uranian magnetosphere.
Yes, at last we've now detected the magnetic field of Uranus and indeed crossed the magnetosphere just a few hours before encounter. We'll be there for a few days, and the first results indicate that the magnetic field of Uranus is stronger than we anticipated, perhaps about a third of the Earth's field.
What about the haze in Uranus's atmosphere?
We've had a chance of looking at it by taking pictures through very special filters. These are filters in the bands where methane normally absorbs. They're very narrow filters. And if there is no cloud there, we would just get a black response because the sunlight will be absorbed by the methane, but a very high cloud will be reflecting. So we can use this as a means of discriminating between high haze layers and areas where there is no haze at all. And this colour picture is done for that purpose. And you'll see a blue crescent, and that indicates the region of the planet that in fact is free of haze. It's not like the colour pictures we looked at in the past, Patrick. And the other thing to notice is that the red ring around the planet is an area where we think there is more haze, perhaps towards the equatorial areas as we look at an oblique angle.
Don't let's forget the rings. Of course, the rings now seem to be of different colours.
Yes, what we're trying to do here is to make a false colour picture to indicate the different reflection properties of the rings. And you can see that quite a wide range of colours is coming out. The Epsilon ring is clearly still very bright, obviously very thick in its opacity. And perhaps it's the different sizes of particles and the thickness of the rings that's causing the colour difference that we can see here. And obviously we'll be learning a lot more about this soon when we get the stellar occultations taking place and we can track the ring thicknesses down to a scale of just a few tens of meters rather than the scales of kilometers we're looking at the moment.
We are now one day past closest approach, and every day brings its new quota of surprises.
Good morning. This morning we communicated to the IAU clearinghouse in Cambridge, Massachusetts, the discovery of one new satellite and one new ring.
Did that surprise you, Gary?
Well, certainly the new ring surprised me. This is the picture of the whole ring system. We can see the very bright Epsilon ring. We can see the less bright and less broad Delta ring. And then when you look very carefully, I'll trace my finger along the edge, you'll see this very faint line. That is the new ring discovered by Voyager. Very faint, very fine, small particles, difficult to observe, but clearly another major Voyager discovery.
What about the new satellite?
Well, again, that's another important discovery, a small satellite. We expect to find many more. Again, small and probably quite dark. We hope to get some more pictures of this in the near future.
I suppose the most remarkable factor today is that the magnetic axis is such a long way from the axis of rotation.
This is really an extraordinary situation. We're finding now that the magnetic axis for Uranus is tipped at 55 degrees from the planet's rotational axis. That already is tipped over at 98 degrees from the plane of the ecliptic. So here we have a tremendous variation between them, and in fact it will give a wobbling magnetic field compared with the way in which we look at the rotational characteristics of the planet.
What about the strength of the magnetic field?
It's very strong. It's about the strength of Saturn's field, about a third the strength of the Earth's field. So it is a very strong field, probably created from the material in the interior. We know hydrogen and helium is there, and we know the rapid rotation of the planet is something like 16, 17 hours. So the dynamo mechanism is certainly creating the field. What we don't know is whether the field, in fact, is what has caused it to be tilted over like this.
We've always thought that Uranus, unlike the other giant planets, doesn't have an internal heat source. Does this mean that it's got one after all?
Not necessarily. It could still have a weak internal heat source. And one other characteristic of Uranus which we've just learnt, which helps us to indicate it does fit into some of the characteristics of the neighbouring giants, is the fact that we now believe it has 10% helium.
Now, if we come on to the satellites, we're getting really good pictures here, and Titania interests me. There's evidence there of tectonic activity.
Well, certainly there's indication of perhaps outflow from collisions, cratering are taking place, and perhaps some brighter material flowing around the edge of the craters.
Titania and Oberon are quite different, aren't they?
Well, yes, and we are certainly seeing the suggestions of, some people think they've described mountains on these particular objects, and I would say that perhaps we don't see mountains just yet. We may be seeing some quite larger craters taking place, but the very best images are not down on the ground yet, they're just coming in.
There's one very curious feature on Umbriel, that kind of donut-shaped thing near the top.
That's very sharp and bright and looking rather like a sort of specular reflecting pattern. I would imagine, that my first guess, and we'll see tomorrow if I'm wrong, that what we're looking at is obliquely at a crater, and that collision has released the brighter material, and of course we're getting a very sharp backscattering coming from that particular area. But certainly we're seeing lighter material coming out onto the surfaces, and these colour pictures, although coloured, are not necessarily the natural colour. We are trying hard to get the natural colour, but at the same time enhance the light and dark contrast with our albedo differences being just a few percent.
We are now 2 days past encounter. Voyager is more than 1 million miles away from Uranus and receding fast. And yesterday we had this incredible picture of the satellite Miranda.
But without doubt, Patrick, it is Miranda that has stolen the show.
Absolutely.
Miranda really is so extraordinary because it has canyons like Mars, it has grooves like Ganymede and compressional faults like Mercury. We've never seen another body like it anywhere in the solar system yet. And you can see in that a whole range of terrain. The albedo features go from the brightest at about 20% and the darkest at 10%. And craters there showing quite a lot of detailed information. And when you look at this particular picture with the groove terrain, you can see the grooves towards the right-hand side of the picture, craters on top of it, obviously indicating that this geological activity has taken place a very long while ago. And our final picture, you may remember at low resolution we saw a chevron feature with a very bright V. This is what it looks at very high resolution. Scarpments there, a lot of linear rills and other intersecting characteristics, particularly towards the right-hand edge. There's probably variations of height there of a few kilometers on one of the smallest, yet one of the most exciting objects we've seen so far. Honestly, Patrick, this must be the highlight of the encounter. This one, for example, of Ariel is actually showing a lot of structure on the surface. In fact, if we saw that picture and thought it was the Earth, we'd think glaciers had moved and in fact covered and produced those smooth areas.
We're now 3 days past closest approach, and Voyager 2 is speeding away from Uranus. It's now reached more than 2 million miles from the planet.
First, I'd like you to meet 1985 U1.
It's about 160 by 170 kilometers. And in fact, you can see a crater there on the object, very dark, but certainly with a very heavily cratered surface. Again, another remarkable success for the engineers who provided this very important scientific result.
As the mission progresses, we're getting back better and better pictures, even of the darkest of the main satellites, Umbriel.
It really is extraordinary because what we're seeing here on Umbriel is that most of the craters are very large, about 100 to 200 kilometers across. And in fact, it seems to be the very old surface with these very large craters on it. So in fact, nothing much has happened in terms of active geology. There is a little bit of light and bright areas. When you see in one part of the picture, a very bright part of a crater sitting up there. But this is probably the oldest surface, the less active surface of any that we've seen so far.
Much older and less active than Titania, for example.
Well, in fact, Titania is rather intriguing. You see loads of small craters, number of rifts there, And in fact, you can see a lot of the bright material coming through the rifts, but certainly a tremendous difference between Titania and Umbriel.
And now, Gary, we come to this incredible picture of the rings. Right. I thought when I saw it that we were looking at Saturn's system, but this really is the ring system of Uranus.
Yes, we're looking at Uranus rings in forward scattering light. So in fact, this is a way of picking up the very small particles that are present. And I think it's very difficult, in fact, initially to be able to relate all the rings you can see. The lowest ring you can see, in fact, is the Epsilon ring, and we're now trying to relate where the others are. And in fact, we probably will be able to pick up a lot of the newly discovered rings and arcs that in fact have been seen. The little long specks which seem to be like raindrops in the rings, in fact, are simply because it's at a very long exposure, which took 96 seconds, and that is a slight bit of motion between the spacecraft and the planetary ring system, giving you these star trails.
Have you any idea of the sizes of the particles in the rings?
Well, the great surprise, Patrick, is how different they seem to be than those we found at Saturn. The Epsilon ring particles seem to be about a meter in cross-section. They may be smaller ones, but certainly these bigger objects seem to be the most likely to be present.
The temperatures on the planet itself are interesting.
Well, in fact, they're absolutely extraordinary because we've now measured the sunlit pole of Uranus and also the dark pole of the planet. And in fact, the temperatures are of a situation that the dark pole, in fact, is slightly warmer, just a few degrees warmer, and that really is very difficult to explain. In fact, we can't really give you an explanation for it at the moment.
How do the equator compare with the poles?
Well, in fact, almost no difference in temperature at all. The only minimum that occurs is about this region between 20 and 30 degrees in the southern hemisphere where the cloud features are seen. That seems to be an area of descending motion, part of one of the major weather systems.
What about the internal heat source? Is there one after all?
Well, we don't have a measurement yet, but perhaps, Patrick, in the next few days, that's going to be the next major discovery.
Well, the pictures are really remarkable. We're just extremely excited about them and the success of the mission. The variety of terrain we see on Miranda is so difficult to explain, of course, but that is exactly where the excitement is. It's always in the unknown and in trying to carry out the detailed analysis.
Has this encounter come up to your expectations?
Well, as usual, it more than exceeded my expectations, and I'm delighted that, the discovery of an oblique rotating magnetic field, of satellites which have really bizarre surface features on them. I think all of these are just the highlights of a wealth of discovery.
It is the integrated set of measurements and their interpretations that will tell us all about Uranus, the rings and the satellites. What we've learned so far is just the start. The next few years are going to be incredibly exciting.
Voyager 2's encounter with Uranus is over. The spacecraft is now speeding on its way to the remote depths of the solar system, leaving the strange green planet far behind. To my mind, one of the most remarkable aspects of this entire mission is that a 10-year-old spacecraft has been used to send us back information from a previously unknown world. In 1989, it will pass by the blue planet Neptune with its strange, huge satellite Triton, which may have oceans on its surface, and sending back, we hope, pictures just as good as those obtained from Uranus. That lies in the future. But meanwhile, we must turn our attention back much nearer home, and to our next Sky at Night special on March the 13th, when I'll be at Darmstadt, the headquarters of the European Space Agency, bringing you, we hope, live pictures sent back by the Giotto probe from the very heart of Halley's Comet. Until then, from here, at the Jet Propulsion Laboratory in California, good night.
There's a second chance to see tonight's Sky at Night programme on Saturday afternoon on 2 at 5 past.